this Saturday morning. I'm Nicole Ferrant. I'm currently the Executive Director of Honua Scholars. We're going to start today with an Oli e Homai. So for those who are able to easily stand, if you can stand up and join me. This Oli is, if you're familiar, you should join in. The words are up here and the translation. As you can see, it's asking for knowledge from above. It seeks all of the wisdom that's around us that we might not always see on the surface. And hopefully that sets the tone for our intentions today to dig deep, to be open to all the knowledge that is held in the individuals present here and that we can share and learn together. So we'll start with this one.
Everyone, please find your seats. Good morning, my name is Kalihua and I'm going to be your MC for today. So, welcome to our 2025 Laulima Symposium. This is going to be our 4th annual symposium and we are very excited to have many new faces along with some participants from years past. So, before we get started, there's a few housekeeping rules. As we know, bathroom is very important. So, right behind here in this little hallway is a men's and women's bathroom, as well as one's located just outside across the hallway too. You can continue to grab food from our beautiful little buffet table as you transition in between sessions. So first, we would like to thank our sponsors who made this event and the Honua programs possible. First, we would like to thank our platinum sponsors, which include Purple Maika and Kumeme Schools, Kaiolu. We would like to recognize our gold sponsors, which include the Pacific Asian Center for Entrepreneurship, the Native Hawaiian Center of Excellence at the John A. Burns School of Medicine, Team Real Estate, and the Abella Ohana. Next, we would like to recognize our silver sponsors. Our silver sponsors, including the Kalino Foundation and L&L Hawaiian Barbecue for donating today's lunch. We also are incredibly grateful to our fiscal sponsor, the Pacific American Foundation, for ensuring that our program continues to be able to serve students. If there are representatives from any of these sponsors in attendance, if you could please stand so that we could recognize you with a round of applause. There are also many volunteers that have helped make today possible, so I'm going to recognize them as well. We would like to thank the Yoshida Ohana, the Abella Ohana, Uncle Herb Lee, our board members, Mr. Manning Tate, Ms. Gail Ishimoto, Dr. Konoho Hosoda, Carmela Biza, Daniel Richardson, Zach Pillian, Tiana Koch, and Nohan Lab. We also are grateful for all of the volunteers who helped judge the student grant proposals in the recent weeks. And then we also want to thank our staff who are contributing to our event today. If you see anybody with a Honua shirt, give them some love, yeah? And then also thank you to all the students who are participating today. in our proposal competition and all of the programs leading up to this event. Without this, we couldn't do what we do for you. We're grateful to the parents and teachers who support these students as well. As somebody who has been both benefiting from that, we appreciate you guys driving, molding our minds. We love it. So we're also happy to be collaborating with you to create opportunities for these students to pursue future careers in STEM. So now we're going to have a message from our Executive Director of Honua Scholars, Dr. Nakoa Ferran, to welcome us. Give him a round of applause.
Aloha everyone. We are so excited to have you all here today. Those returning from previous symposiums, all the new faces as well, we're so grateful to you all. I was talking with our Executive Director Emeritus, Kyle Yoshida, yesterday about just how far Honua Scholars has come since 2020. This really was Kyle's brainchild and an idea for how, recognizing that many of us on the Honua staff had tremendous support in high school, and it enabled a lot of opportunities to follow, and trying to create more opportunities for other students to have the same, support teachers who are pushing to do that as well. And so that's kind of the birth of our program, really focus on creating opportunities for students to share their big ideas to address challenges in our communities, to network with individuals in STEM across academic universities and industry, and our government agencies, to hopefully recognize that there is opportunities for diverse STEM futures here in Hawaii for them, and that they don't necessarily all want to leave to find those opportunities elsewhere. For those who aren't familiar with some of our programs, we have monthly dialogue sessions with some of those types of speakers. Those are held on Zoom on every third Wednesday. So please join us in the future if you haven't before. Again, featuring many people often with connections to Hawaii across an array of STEM fields to identify these different pathways, create opportunities for potential mentorship. Another central program of Honua Scholars is our proposal competition every year, where students submit a 1 to 2 page written proposal about an idea that they want to address in STEM. And today you'll be hearing some of those students pitch. We're so happy to see many of them turn out with their teachers, with their families. So thank you for coming and all the support you provide to these students, to collaborate with us to try to continue supporting them in their pursuit of their dreams and ideas. What's really special, I think, about Laulima Symposium is it's this microcosm of a day that hits on so many of these core values of Honua Scholars, where we have the opportunity to bring together community members involved with STEM, with students, to have this close interaction and exchange of ideas, create possibilities for potential mentorship or internships, recognize students with some awards, give them practical skills in writing and presentations, and hopefully many more benefits as well. Hopefully many of you will find our keynote today very inspiring. I'll now welcome Dr. Kamwela Young to the stage. So we are very excited for our welcome our keynote. Dr. Kamwela Young will be presenting his talk entitled My Voyage in Mathematics. Dr. Young is a native Hawaiian mathematician who grew up in Waimanalo, who now teaches at the University of Hawaii, West Oahu. He earned his PhD in mathematics and became the first native Hawaiian to do so. His work focuses on connecting math to Hawaiian culture so that students can see how mathematics is part of their everyday lives, history, and community. Dr. Young develops math lessons that include stories of voyaging, navigation, local traditions to show that mathematics is not just about numbers, but about understanding the world around us. He hopes to inspire the next generation of learners to use their knowledge to care for their people and place. Join me in welcoming Dr. Kamwela Young.
Good morning, everyone. It's really nice to see all of you here and to hear that you all are getting really engaged in research and learning about it, and some of you are sharing about it. That's really great, and that's something that I kind of wish I had done way earlier. But I'm going to share with you this morning sort of my journey, the path that I took to get from when I started college and to where I'm at right now. So yeah, let's come along as we go in my journey. All right. So I was a really math-oriented person. I liked math, and I thought, okay, well, what's a career of this? Someone who does math and wants to go do problem solving. And so I thought engineering. And I remember in 10th grade, we did a report in English on what kind of career you want to be. And I knew from then I wanted to be a civil engineer. And so I chose to go to LMU, Loyola Marymount University in Los Angeles. There I enrolled as a civil engineering major. In engineering, you take a lot of math classes, and I took a whole lot of classes. If I took just 3 more classes, I'd get a minor in math. So I'm like, sure, I'll do that. Like, why are you gonna get a minor? I don't know, it might look good. Sure, I did. And then I took more than 3. And then when I was like, well, I guess if I just take like 5 more, I'm gonna get a 2nd degree. So I took 5 more classes, like after the 3. Yes, I took more, and I got 2 degrees, one in civil engineering and one in applied mathematics. At the time, people were like, what would you even do with a math degree? I had no idea. Like, you'd be a teacher? That was really the only thing I knew. But applied mathematics was just this. It was a whole world that I didn't know. And at LMU, I had a really wonderful mentor. And this mentor, she showed me like what you could do with applied math and with research. And so everything from you can create models to model the spread of an invasive species, to looking at the way ideas spread, to the spread of diseases, to climate change, so all sorts of things you can model with math. You use math to explain things that are rooted in science and sociology, and all these things around us, math can model these things. Wow, that's really cool. So I started doing research with my mentor, and in a while ago, I guess, I was younger, and cameras weren't as good quality as they are now, but it was like the first generation of digital cameras. Okay? Along with one of my classmates, we presented at a national conference, and that was a really great thing. And what we did was we modeled the spread of ideology within the spread of ideas in Los Angeles. And so we used like data from census to see what the different population makeup was, and create these models, and that was really interesting. But before that, this problem, we were able to take like a problem that we came up with on our own, and we found like what's the math that we need to do, and we did this, and it was a really fun thing. And before I thought scientific research was just a lab report, which is not really research. You're just doing these steps. But I didn't realize that, and once I did that, I was like, this is really fun. I could do more. And so now I'm like, well, maybe I want to go and do more and get a PhD, get a doctorate, and continue this research. So I started looking in math and in engineering programs, and then I started to think, what I really liked at that time was looking at like a series of dams, hydrology. If you have all these dams and it controls water as it goes along, if it floods, if you hold too much upstream, it's going to flood upstream. But if you let all that water down, it's going to flood downstream. So this is, in math, we call it an optimization problem. Like, how would we control that? I thought this is great. And so I started looking at math and engineering programs, and I ended up choosing a math program because I could also continue taking engineering classes in that math program. And I chose Iowa. Does anyone know where Iowa is? Okay, 3 of you? Okay, 4 of you? Yeah, I actually didn't know where it was on that map when I was like talking with Iowa. Okay, so here's Iowa. Now I'm in Los Angeles. On the plane, we went over Iowa to Chicago because the Iowa airport, like you could actually park at the airport and then like walk in like on that curb, and then like in 5 minutes they'll call you like, the white car, can you please move your car? They don't have like the airport security just like blowing the whistle, like, if you like stand for like 20 seconds. But so that was Iowa. And when I started to go there and stop identifying as an engineer who did math problems to being an applied mathematician to do applications, I was like, well, that engineer problem is great, but like, what are other things that I have passions for? And I had a passion for ecology. I would never be an ecology major. I don't think that was my thing. Like I was really good at math, and that was the way that what I had a passion for, or what I enjoyed. But I had another passion for ecology, and so I could create mathematical problems for ecology. And that was really cool. That was how I started to identify. But so I went to the University of Iowa, and I thought, when I was an undergrad, I double majored. I took a lot of math, a lot of engineering classes. In fact, I took so many classes that if you averaged it out, it would be over 5.5 years of college that I crammed into 4 years. Like, I was just that kind of kid. So I'm like, okay, I can do this. Like, I can do grad school. And my first day in class, they covered my entire undergraduate course in an hour. And I'm just like, oh wow, this is very different. This is very different, not the way I thought it was gonna go. And then it didn't get any better. I only took 3 classes in graduate school, but those 3 classes were brutal. And then I started looking around. Nobody was asking questions. So everyone around me was like, they had no questions. They obviously knew what was happening, and I felt really, really bad. Like maybe I made the wrong decision. And I called up my mentor, and we talked for a few hours one night. And then I talked to another student that was a year ahead of me, and I realized that the reason why the person next to me, why she wasn't asking questions, and the person on the other side of me, why he wasn't asking questions, so they weren't asking questions, so I didn't want to look like the only stupid one, so I didn't say anything. But then they're looking at me like, wow, this guy knows what's happening. He has no questions. And then next thing you know, it's like, wait a minute, we all are lost, but no one wanted to ask a question? Like, that's what happened, was that we were all lost. No, we didn't know what was happening, but we didn't want to look like the only one that did. And there's like one student who confidently asked like these really smart questions. It was so smart, I didn't know what the question was. So I felt really bad. Now as a teacher, sometimes those really smart questions they don't actually know what they're doing, they just ask it very confidently. Like, now I have a doctorate and I don't understand those questions. So sometimes when you're in class and you hear some questions like that and you feel like you don't understand, it's not because of you, sometimes it's because of them. So just kind of keep that in mind. Like, and if you feel like really lost and no one else is saying anything and you think they understand, it might be that they're looking at you because you are also not seeing anything. And it can be really tough. And it came to a point where I almost thought I didn't belong and I made a wrong decision and I should have dropped out. But I talked to my mentors, I talked to other people, and I realized that no, like it's tough. And the reason why there's not a lot of people that go to graduate school is because it's just a tough thing to do. It's a tough thing, but with the right help and the right support, we got through it. So I started to do that. Classes weren't fun, but I got through it. Okay, I got through it. And then we had to take these qualifying exams, and I didn't pass it the first time. And and I spent the whole summer, I didn't go home, I stayed in Iowa the whole summer, and I studied the whole summer, and I didn't pass it, and I have one more chance if I took it again, and if I didn't pass it, they'd kick me out of the program. And so you have to get like a PhD level pass, a master's pass, or no pass. And I got master's pass on them, but not PhD, and so I had to retake them to get a PhD level pass to continue on to get my PhD. So it was another setback, which I thought, this, you know, what am I doing here? I just gave up a whole year in Iowa. I gave up my summer. I didn't even go home. And, you know, like, am I making the right decision? But again, I talked to people, I got help. Once I passed those things, I was able to now have the freedom to start doing things that I wanted to do. In terms of the research, there are some things that you just need to, like, you have to do certain steps, and then you can start really engaging in the things that was really fun. So after that point, one, starting to feel like I didn't belong in the classes, then I talked to people, I got help. Then I felt like I didn't pass these tests, you know, and I was gonna get kicked out, but I kept going through it. I talked to some professors, and I got through, and then things started to go downhill. It was like, remember, this is Iowa, so it was cold. The coldest it's got was like 20 something below zero. So it got pretty cold sometimes. But things started to pick up. Okay. I was the first person in my cohort to propose their thesis topic, and my thesis topic was modeling bee pollination in almond orchards. So I created these math models to show how bees pollinated these almonds. And an almond is a multi-billion, just the California almond industry, it's a multi-billion-dollar industry. And so if we can model the way bees are moving and pollinating, and we can adjust it just by a small increment, make them more efficient, that multi-billion dollars is a huge money increase. And so that was what my thesis was. I was the first to propose that. I got to leave Iowa and go to California in February during the pollination season to observe these bees. As a mathematician, I was doing field work. And so that was really fun, especially when I left, you know, and it was still like snow on the ground, and I go out to California. So that was a really fun thing. But then I was the first to propose my thesis. I was the first to schedule my defense, because I started to engage in things that I really wanted to do. And so there were tough times, and I got people, and I talked to them, the people that needed to help me. They helped me get through what I needed to do. Then I started to have the fun things. I did this, and then I even was the first to get offered a job outside of the university. So coming back thinking when I first started that I didn't belong, no, it was just, these are hard things to get through. Because I do belong, and look at me excel. I'm the first to start doing all these things because I'm finally finding my passion. Sometimes it's a while before you find the things that you are really passionate about. But to get there, there's a whole network of people to help you out. So I got my PhD in applied mathematics, becoming the first ever native Hawaiian to get a PhD in applied mathematics. Afterwards, I went to Arizona State, where I worked for a few years before being able to move home. I moved to University of Hawaii, West Oahu. I live in Waimanalo, but I work in Kapolei. It's okay because the sun's behind me the whole way, so that's a nice drive, and the traffic's on the other side of the freeway, so sorry for all of you West Side people. But I love it out there. And at UH West Oahu, I started to do research with students. And I brought students, now full circle, taking students to conferences. And so these are my first students that I took to conferences, actually that's their second conference I took them to. But we began going to conferences, doing research with students, the same way that my mentor did with me. And here's another picture. But when I started at UH West Oahu, people were really excited because they said, great, you know, we have a Hawaiian mathematician, you must know ethnomath. You must know math through a Hawaiian cultural landscape. And I'm like, well, I didn't really quite learn that in Arizona or Iowa or LA. So I'm a Hawaiian, I'm a mathematician, but I don't do Hawaiian math. So the next part is I'm gonna take you on my personal journey when I transformed my math curriculum and other math curriculum to include more cultural relevant materials. So this is the Hawaiian Star Compass. Has anyone heard of the Hawaiian Star Compass? Some of you have heard of it. I know, folks, you know that well. Actually, I worked with you on it. Okay. So, the Hawaiian Star Compass is an adaptation that Nainoa Takasaki made from the Micronesian puff. The Hawaiian Star Compass, just looking at this, it's overlaid very similar to the 32 Rose Compass. There's like east, north, southwest, southeast, all these different things. But looking at this, notice anything from just looking at, and so he laid them out. There's 4 quadrants, and they're named after the different winds, the 4 major winds in Hawaii. And then within them, there's houses, and these houses are sort of like this, like real estate of the sky. Like this part would be, like Aina, and this part, it's all broken up into just different sections. But you notice the house names are repeated in each of the quadrants. And one of the things that I took from that is that we can take this star compass, and if you start getting familiar with the star compass, we can introduce for like upper elementary the XY axis, the Cartesian plane. And because let's say you're in the center and you walk 3 steps to the right and 2 steps up, 3 steps east, so we can talk about east-west in terms of the x-axis. Just our math, north-south in terms of the y-axis. And if you go 3 steps east, 2 steps north, you're in Aina. 3 steps west, 2 steps north, 3, 2, 3, 2. We're all in the same house, Aina. And that's all 3 and 2. And so I say the only difference between that is that we're going 3 east-west. We need to determine which one is east, which one is west. We call them positive or negative x. Same thing for y. And then you can show pictures that do that. And in class, they would normally draw a picture of like a house or a Christmas tree. You can draw canoes. There's symmetry. So we can introduce the concept of symmetry. The star compass has that symmetry because if you're on the canoe and wind is coming from one house, the way it enters the canoe is the same place where it exits the canoe, the same house, or wind. So wind or current or swells. So these are the things that you can feel and you use them as navigational techniques. In trigonometry, if you're in trigonometry, there's the unit circle. And students have a hard time understanding the symmetry within the unit circle until I start to relate it to this physical thing, that it's the exact same. The 30 degrees above the x-axis is root 3 over 2, 1/2. 30 degrees below is also root 3 over 2, 1/2, and all the same. And now this thing that students have a hard time understanding, through relating it to these physical aspects, become really more attainable. I started looking at textbooks. This textbook problem is saying word problems, right? We love word problems, don't we? No, oh, okay, well, maybe it's just me. This word problem says that you're in Maine. You're on the east coast of Maine and top of this mountain. You're the furthest point east on the continent of the United States. You're on top of the mountain, so we're higher up. You can see the sunrise faster than anyone else in the continental US from on top of this mountain. How much faster would you see the sunrise on top of the mountain than the bottom? I, being the nerd that I am, thought that was pretty cool. Maybe the way I explained it is kind of fun for you now, but I was like, well, shoot, we have bigger mountains than this. This mountain is only 1,530 feet. That's like a pimple. Mauna Kea is almost 14,000 feet. So how much faster? Turns out, if you see the sunrise on Mauna Kea, you can see the sunrise in 8 minutes, almost 8.5 minutes faster than someone down at Hilo, because you're so much higher. And in fact, on top of Mauna Kea, you can see your horizon is 144 miles. So you might notice, like when you're down at the beach, like the horizon's running like this. But when you're coming over the Pali or the H3, the horizon's like this, right? You can see a whole lot more. And that's because of this whole thing that plays into effect. I thought, well, Haleakala, another tall mountain, you can see sunrise 7 minutes in 123 miles. And I went, well, we could actually relate this to Mo'olelo, the Mo'olelo of Maui. And you talk about the sun moving so fast, and Maui climbs the top of the mauna and to snare the sun. When he is waiting for the sun, how much faster would he see the sun than someone down, at the sea level? So we can start taking that. But then I said, well, instead of from the mauna looking to the horizon, what if you're sailing and trying to see when you first see the mauna line up with the horizon, when you're on the wa'a? And so this is what's happening. The mo'olelo is that Maui pulls the island out of the ocean. This is what they're seeing on top of the canoe. But this is the mechanics that's happening when you first see that. The exact same framework of this original work problem is now explaining what happens on the canoe. So what I did is I turned this into a work problem, and I'll summarize it. So you're on Hokule'a, you're sailing to Rapa Nui, and you know through a process called dead reckoning, which says how far you've gone. And you can measure that by your speed and how much time, right? Speed is distance over time. If you know your speed and you know your time, you'll know your distance. The latitude sailing, stars will tell you what latitude you're at. So you know you're at the right latitude of your destination. You know how far you've traveled, so you know you're near. You start looking for signs of land. Land-based seabirds, the Manuoku only flies a certain distance and comes back every day. So if you're within their flight range, you know you're within land. The clouds have different colors over a blue lagoon versus green land versus the deep blue ocean. So if you see clouds have different colors, that's another indicator. Sometimes you'll see vegetation drifted off. You'll see coconuts floating around. So you know you're getting near. In fact, even like the waves will hit the island and they'll ripple off, and you'll feel this different. After weeks on the ocean, you have the same swells, and then you have this different bump, and that's because now you know it's that bouncing off. And you've maybe seen those models of like when like the tsunami hits and they kind of spread out, but when it bumps into the island, it kind of has that ripple. If you've seen those animations, that's what's happening. So you'll feel that. So with that said, when do you first see land? Now this is a math problem. This whole thing, talking about introducing this concept of that. And so when do you first see land? Giving this whole story. And when I first did that, I made the mistake of saying we're sailing to Tahiti. So I'm just reading in the books and on PBS's website, Polynesian Voices Society, what they look for, and so I'm trying to do this on my own. But when I said we're sailing to Tahiti, the thing is, you never actually see the island before you get there. Tahiti is surrounded by atolls. So when you go to Tahiti, you're gonna run into the atolls, and then then you'll see Tahiti. So like that. So I changed the problem to Rapa Nui, the most isolated island in the world. But it made me realize that I need to, if I'm talking about canoe culture, even though I am Native Hawaiian, I am not in that culture now. And so I wanted to make sure that I worked with that community to learn, to make sure I'm doing it right, and understanding how they do it, and work with them to make sure that I'm not some outsider writing about them without their permission. So I started to work with this community, but it unlocked this whole new aspect of things. There's a problem called, you spin something in a circle, and it's like, how fast is it moving? It's called angular speed and linear speed. And the problem saying, like, point on the tire is spinning, how fast is that moving? Or a kid has a rope on a rock and they're spinning it around their head. Well, like, who has a rope on a rock on a rope? You're like, what? I've never understood that. Ferris wheel, okay, how fast are you moving on the Ferris wheel? I took that and said, there's a whole bunch of cultural aspects. In fact, this problem came from a woman who came from Egypt, and she asked her students, is there something that you do that spins around? And one of her students danced, and so koi balls. So you can be like, you can measure how fast a koi ball is moving next to your head. And I think that'd be a really fun thing to do. You're like, yeah, I'm gonna go fast koi, it's like 40 miles an hour right next to my face. Pretty cool. We could measure how fast it is by looking at the length of the string and how many revolutions per minute, or you can count for 20 seconds, and then just do conversions. The oi oi is a bull roar. It makes a little whistling noise. This other thing, on the canoe, we have to, it's called une, you're turning. So I measured how fast I was going, how many revolutions in like 20 seconds that took me, and that was about like 4 feet, I would say, from the shoulder to my knee. And then, yeah, the other things is the Earth. We spin around, we make one full rotation in 24 hours. Okay? So here in Hawaii, we're spinning around like 900 miles per hour. Because we have to go around the whole Earth in one day. We make one full revolution. Closer to the equator, they're going at like 1,100 miles an hour. But we don't feel it. Like when we're in the car, do we really like, you know, our drinks aren't sloshing because everything is moving. The air inside the car, you don't even feel the wind unless you can roll down the window. So honestly, the whole Earth, everything's moving. So we don't feel moving at like 1,000 miles an hour or 900. Unless the Earth stops spinning. It's like, you know, when you're in a car, you're going really fast, you're going 60 miles an hour, and then if you hit a brick wall, then you stop and you can feel that you're moving 60 miles an hour. So if the Earth stops spinning, the Earth would stop, and then basically everything would just go flying off at 900 miles an hour. But that's a pretty cool thing. So I started to look at the world around me and find, how can we explain things? Here in Micronesia, they have another process called etok, which is moving islands, and what they do is basically the canoe is stationary, and everything else moves. That's how they view their world. The canoe is stationary. They pull the island to them. They push the island away from them. And so if you're going to Guam, we can sort of think of this in like with law of cosines, because they know as they go how far they brought the island to them, how far they moved the island away. So we can explain that thought process using law of cosines. And then the last thing I want to talk about is vector addition. And so vector addition, this is the standard textbook. You have one vector and two vectors, and you line up the end of the first vector and the start of the second vector together. And the vector addition is where one vector starts and the second vector ends. That's what vector addition is. You can get but I now introduce vector addition by saying we're sending from Tahiti to Hawaii. We use latitude sailing. So if we go straight up from Tahiti, straight north to the right latitude of Hawaii, the stars are always moving east-west. We can't tell how far we are east-west, but we can tell how far we are north-south. The stars are going to be in different spots, especially the North Star. The North Star corresponds to our latitude. So in Hawaii, and you always see like, you know, those pictures like Moana and like they're measuring the sky. What they're doing is they're looking at the angle of the stars. And so if the stars are at the right angle of Hawaii, then we know where we're at. And then, so you sail straight up till you hit Hawaii, and then you hit west, and that's it. So the vector addition of the north path and then the west path is our route from Tahiti, ending in Hawaii. So that's what we would do vector addition. And then I have my students actually do charting. They'll chart a course using vectors for that. But there's math all around. You can, instead of having just a problem where you talk about like the angle of a roof, we can learn about indigenous architecture from around the world. But there really is math all around. I would love to talk more, but I do have more examples on my website, as well as I have a free textbook, math trigonometry through Va'a. It's all on my website, kamoalayong.com, if you need it. But yeah, are there any questions?
Mahalo nui, Dr. Young. That was a fantastic keynote. So many amazing messages. I'm looking forward to your mentors to support you through some tough challenges that are inevitably ahead. Identifying ways to connect culture to your passions and various STEM disciplines, creating resources for students and teachers to use as well. So mahalo nui for that work. Sounds like we maybe have time for 1 or 2 questions if anyone has any. I can pass the remote or the microphone around. Okay, we got one here.
Oh, sorry, Doctor. I always have questions about what is the one takeaway? Because you have these incredible professors and you have these challenges like, oh my gosh, am I the only one who doesn't get it? Because I've been in the same place too. What is the thing you take away now that you're the professor? The roles are switched now, these new people coming to you. How did you modify that to now be, maybe have the, how are you approaching their learning maybe differently than you would tell?
I mean, I think the thing is we look at people and we look at where they are now. We don't see what it took to get there, and the thing is, like, we're proud people. We don't want to be like, hey, guess what? I failed this test, like, you know. So we don't really talk about that, but we're like, hey, guess what? I graduated. Like, those are things that we want to talk about. So you see all those things, and just there's so many productive struggles that we got to get here, but we don't really share those. It's not normalized, and so you don't really hear those things, and you only see all the finished product. You know, as soon as you see your professors and teachers, and you're like, wow, they must know what they're doing because they're here in front of me today. You don't know that, you know, all the times that it took to get there. Like, it's really hard. And so one of the things that really helped me was recognizing that, you know, we're not going to be bragging about things that was hard for us. And it's kind of hidden. And finding someone that you trust to talk to. So finding someone who's been there, who's done it already. For me, it was a professor that's on the other end now. Finding a classmate who was a year ahead, who was like, oh yeah, that's a hard class. No one understands what's happening there, but no one's gonna say anything. Okay, so like those, and then I found someone in my class that I could work with. So, you know, there are, it's hard. You don't really see all of the things, because, you know, you look at me and you're like, wow, you know, he's really well put together. He's got his doctorate, you know, he's got like whatever, they do all these things, but that's because you see the end thing. You know, I don't put it in my introduction, nor did it say he didn't pass his qualifying exams the first time. You know, he almost dropped out. Like those aren't in my introduction in the bio. We talk about our accomplishments, and so people think that you have to be really smart and gifted to go to college or to go to graduate school. It's not really that, it's the not giving up and using the resources. Because I don't consider myself to be, you know, a genius. I just consider myself to utilize the resources that I have to get to where I need to be. So, yeah.
Thank you.
Mahalo nui kamoala. I will ask you to head out to, Ashley.
It seemed like there was a lot of overlap between navigation and applied mathematics, which you've noticed so far, but are there any other areas within the Native Hawaiian culture that you kind of been noticing that you wanted to explore next?
Oh yeah, it's all over. So first of all, there's no traditional word for mathematics in Hawaiian. So we do have the word makimakika, but that's a modern transliteration. The thing is that Native Hawaiians were practicing math in everything they did. So just think about like the mahi island, the farmer. You know, if you've ever gone to the Laulima and the farmer's like, okay, we're gonna get 200 pounds today. Well, why? Well, they've done it because they've done it a lot. But maybe it's because this corn is a 2-pound variety, and we're gonna harvest 2 rows, and let's see, I'm trying to think of numbers off the top of my head, or easy numbers. We're gonna harvest, 2 rows of 50. Okay, so there's gonna be 50 plants in each row. So that's 2 times 50 is gonna be 100. So you're getting 100 roots, and each root is 2 pounds, so we're gonna get 200 pounds. They're not doing those calculations, they're doing it because they know it, but then that's in here. If we have a bumper crop year, then they're like, oh yeah, we're gonna get like 230 pounds this year. Or if it's, you know, bad weather, then it could be like 180. Like they know it because they've done it, but we can do math to describe it. If you go out there, then they're like, okay, we're gonna need about 5 wheelbarrows load to throw the column in there and then wheel it up to the shed. Well, how do you know? Well, maybe because a wheelbarrow holds 20 roots inside of it, and then like we can find math to understand these things, but it's really in everything, in like in kapa making, in hale building, like it's all over. And I'm just scratching the surface. I'm just like I spent a lot of time in the last 4 years exploring Va'a, and now I'm trying to find other work with practitioners, because I have the math ike, but practitioners have the ike in what they do, and so kako together, learning from them, they share what they do. You know, then it becomes then we can create and find the math that's behind it. Like I remember one of the captains I said, he's like, oh, I'm not a math person, but he was like, I guarantee we'll go from Lahaina to Waikiki, we'll be there by 7 p.m. But he knew the exact mileage from each point to each point, like to this part of the island, to this part of Lanai, to wherever, and he knew the wind, and so again, you know the distance, and you know the wind, so you know your speed. He knows, like he knows that, and then he knows the time. But he's not calculating that, he just knows it because it's in here, they've done it. And so just working with these knowledge holders are what I do to try and bring out the math behind that.
All Pamuela. We know you have to head out, but of course, as Kamala mentioned, his website, kamalayoung.com. If you want to look for his resources, he's generously sharing. We can help to connect you if you see an opportunity for Kamala to maybe play a role in mentoring you or collaborating. Again, just join me in one more mahalo for Kamala.
Awesome, guys. Thank you so much. So let's transition into the next part of our program, the proposal pitch presentations. So this summer, Winona Scholars released its 4th annual proposal competition. This year, there were over 100 entries from 14 different schools from 5th grade through college. And this year's theme was Keola Pono. So we were interested in submissions that related to some aspect of individual, community, or environmental health, or holistic well-being, which could take many forms. Students submitted a 1 to 2 page proposal for one of 3 categories, either a science experiment, technological intervention, or a persuasive advocacy piece related to our theme. So today we welcome 27 students who will use up to 2 minutes to pitch their project. So after each pitch, we're gonna have time for 1 to 2 questions. Today we have several judges who are researchers, community leaders, professors, and teachers. So they're going to be selecting the winners from these pitches. Furthermore, you, the audience, will be able to vote as well for your favorite project at the end of the session. So keep an eye out for your favorite projects. Moderating this session will be Kyle Yoshida. Right over there. There we go. Give him a round of applause, guys. So, last year we were able to fit all of our presentations in one room, but this year, to accommodate 8 more pitches, student presenters will be split into 2 rooms. So up here, find your name. If you see your name under room 1, you're gonna stay in this room, okay?
Sorry.
Wrong one, not correct?
Full script, sorry.
Got it.
So as it shows on the slide is accurate. Sorry, Kalikoa, that was my fault. So group 1 will go to room 13. Courtney here in the back, and